What if I told you there's a thinking method so powerful it built every piece of modern technology you use? Your phone, your car, the medicine keeping your grandparents alive. And yet, this method has been attacked, dismissed, and practically erased from how we're taught to think. For over a century, philosophers have called it invalid. Scientists use it every single day but can't explain why it works. And you were never taught it in school. Today, we're going to uncover the forbidden logic that changed everything. We're going to follow the trail from a man dropping balls off a tower in Italy to the most powerful equation ever written, to why modern physics might be completely lost. And by the end of this video, you're going to understand something that most scientists themselves don't. Stay with me. All right, let's start with the basics, because if you're like most people, you've probably never heard this term used correctly. Induction is the process of reasoning from specific observations to general principles. You see something happen once, twice, 100 times, and then you make a leap. You conclude that it will always happen that way. Here's the thing. Every single scientific law we have came from this process. Everyone. When you learned that water boils at 100 degrees Celsius, that wasn't handed down from some divine source. Someone had to heat water, measure it, do it again and again, and then make the leap that it would always boil at that temperature under those conditions. But here's where things get weird. Philosophers have been arguing for centuries that this leap is logically invalid. They say you can't prove the future will resemble the past. You can't prove that just because something happened 1,000 times, it will happen the 1,001st time. This is called the problem of induction, and it was first clearly stated by a Scottish philosopher named David Hume back in the 1700s. Hume essentially said that all inductive reasoning is fundamentally unjustified. We do it out of habit, not logic. And here's the really strange part. Most modern scientists and philosophers accepted this critique. They basically shrugged and said, yeah, we can't justify induction, but we use it anyway because it works. Does that sound like a solid foundation for all of human knowledge to you? Let me take you back to Italy. The year is 1589. A young professor named Galileo Galilei is about to do something that will change human history. For nearly 2,000 years, everyone in the Western world believed something that Aristotle had written. Aristotle said that heavier objects fall faster than lighter ones. It made intuitive sense, right? Drop a rock and a feather, the rock hits first. Case closed. But Galileo wasn't satisfied with intuition. He wanted to see for himself. Now there's a famous story that Galileo dropped 2 balls of different weights from the Leaning Tower of Pisa. Historians debate whether this actually happened. But what we know for certain is that Galileo did conduct careful experiments with falling objects. And here's what he discovered. When you remove air resistance from the equation, all objects fall at exactly the same rate regardless of their weight. A cannonball and a musket ball hit the ground at the same time. This was revolutionary. But here's what most people miss about this story. Galileo didn't just observe that objects fell at the same rate. He made a leap. He concluded that this would always be true everywhere in the universe, for all objects, for all time. He generalized from a limited number of experiments to a universal law. And he was right. But how did he know he was right? How could he possibly justify that leap from a few experiments to a claim about the entire universe? This is where it gets interesting. Galileo didn't just randomly guess. He identified something crucial. He identified the causal relationship. See, Galileo understood that what makes an object fall is not its weight in the sense of how heavy it feels. It's the relationship between the gravitational force acting on it and its mass. And since gravitational force increases proportionally with mass, the acceleration remains constant. He grasped the why behind the what. And that's what made his induction valid. But Galileo wasn't done. He went further. He studied motion on inclined planes. He rolled balls down ramps of different angles and meticulously measured their acceleration. And from these experiments, he derived the law of uniformly accelerated motion. This was the birth of modern physics. Not because Galileo made observations. People had been observing nature for thousands of years. It was because Galileo understood how to make the leap from observation to law. He understood induction. Now let's jump forward about a century. A young man in England is about to take Galileo's work and transform it into something even more extraordinary. Newton took Galileo's laws of motion and asked a deeper question. What if the same force that makes an apple fall from a tree is the same force that keeps the moon in orbit around the Earth? Think about how radical that idea was. The heavens had always been considered fundamentally different from Earth. Celestial objects were supposed to follow different rules. But Newton made a leap. He proposed that one single force, gravity, governed both the apple and the moon. And then he proved it mathematically. Newton showed that if you apply the same gravitational force to the moon that you apply to objects on Earth, adjusting for distance, you get exactly the orbital motion we observe. The numbers matched perfectly. This was the law of universal gravitation. And the word universal is key here. Newton wasn't just saying gravity works on Earth. He was saying it works everywhere, on every object, throughout the entire cosmos. That's an enormous inductive leap. Newton had only observed gravity on Earth and calculated the moon's orbit. Yet he claimed this law applied to stars he couldn't even see, to galaxies that wouldn't be discovered for centuries. How could he justify such a claim? Here's where we need to understand something crucial. Newton didn't just notice a pattern and assume it would continue. He identified the essential nature of mass and its relationship to gravitational force. He grasped the causal mechanism. When you understand why something happens, not just that it happens, you can legitimately extend your conclusions beyond your immediate observations. That's the key to valid induction. And Newton's law held up. For over 200 years, every observation confirmed it. When astronomers noticed that Uranus wasn't moving quite right according to Newton's equations, they didn't conclude that Newton was wrong. They concluded there must be another planet affecting its orbit. And when they pointed their telescopes where Newton's math said a planet should be, they discovered Neptune. That's the power of valid induction. It doesn't just describe what you've seen, it predicts what you haven't seen yet. But here's something most people don't know. Newton himself was very clear about his method. He famously said, "I do not feign hypotheses." What he meant was that he didn't just make up theories and then look for evidence. He started with observations, identified causal relationships, and then generalized. This is the opposite of how most people think science works today. Let's fast forward again. The 19th century. Scientists are making another massive inductive leap, this time into the invisible world of atoms. Now, the idea of atoms wasn't new. Ancient Greek philosophers had proposed that matter might be made of tiny, indivisible particles, but that was just speculation, pure philosophy, without evidence. What changed in the 1800s was that scientists started finding actual evidence. And more importantly, they started understanding the causal relationships. John Dalton proposed his atomic theory in 1803. He noticed that when elements combine to form compounds, they always do so in fixed ratios. Water is always 2 parts hydrogen to 1 part oxygen. Not sometimes 2.1, not sometimes 1.9. Always exactly 2 to 1. Why would that be true unless matter was made of discrete particles that combined in whole number ratios? Dalton made the leap. He concluded that atoms were real, that each element had its own type of atom with a specific weight, and that chemical reactions were just atoms rearranging themselves. This was induction at its finest. From the observed regularity of chemical combinations, Dalton inferred the existence of entities he couldn't see, touch, or directly measure. And he was right. Over the next century, evidence piled up. Brownian motion, the random jiggling of particles suspended in liquid, was explained by Einstein as atoms colliding with those particles. Radioactivity revealed that atoms had internal structure. X-ray crystallography showed atoms arranged in precise geometric patterns. Each new discovery confirmed and extended the atomic theory. The inductive leap held. But here's what's remarkable. At every stage, scientists weren't just collecting data. They were identifying causal relationships. They were asking why. Why do elements combine in fixed ratios? Because atoms are discrete units. Why does Brownian motion occur? Because invisible atoms are striking the visible particles. The why is what makes induction valid. Without understanding causation, you're just pattern matching, and pattern matching can lead you astray. All right, here's where things get weird, and I mean really weird. Because something happened in the 20th century that derailed this entire process, and we're still dealing with the consequences today. It started with quantum mechanics. When scientists began exploring the subatomic world, they found things that didn't seem to follow the rules. Particles that seemed to be in two places at once. Outcomes that appeared genuinely random. Observations that seemed to affect what was being observed. And instead of doing what Galileo and Newton did, instead of digging deeper to find the causal relationships, many physicists gave up. They adopted what's called the Copenhagen interpretation. And this interpretation essentially says, don't ask why. The math works. Just use it. Don't try to understand what's actually happening at the subatomic level because it's fundamentally unknowable. Do you hear how different that is from everything we just discussed? Galileo asked why objects fall at the same rate. Newton asked why the moon stays in orbit. Dalton asked why elements combine in fixed ratios. They demanded causal explanations, and they found them. But with quantum mechanics, a generation of physicists essentially said causality doesn't apply at the fundamental level. Reality is inherently random. Shut up and calculate. And this attitude spread. It infected cosmology, where theories about the origin of the universe became increasingly detached from observation. It infected string theory, where mathematical elegance replaced experimental validation. Today, we have theories in physics that make no testable predictions. We have interpretations that deny the very possibility of understanding. We have a field that has, in many ways, abandoned the method that built it. This isn't me being controversial. This is a recognized crisis within physics itself. Experiments like the Large Hadron Collider have failed to find the particles that dominant theories predicted. The field has been stuck for decades, and according to the analysis in the logical leap, this crisis traces directly back to abandoning proper inductive method. When you stop demanding causal explanations, when you reduce science to mathematical formalism, you lose the ability to make genuine progress. So what makes induction valid? How do we separate legitimate scientific reasoning from mere guessing? The logical leap proposes 3 essential criteria, and understanding these criteria is the key to understanding why some scientific theories hold up and others collapse. First, every concept and generalization must derive from observations through a valid method. You can't just make things up. You can't start with a theory and then cherry-pick evidence. You have to build from the ground up, from what you actually observe. This sounds obvious, but it's violated constantly. When physicists propose 11-dimensional spaces that can never be observed, they're violating this criterion. When cosmologists propose infinite parallel universes based purely on mathematical possibility, they're violating this criterion. Second, the theory must form an integrated whole where all the parts mutually reinforce each other. This is crucial. Valid induction doesn't just produce isolated facts. It produces a coherent system where each piece supports the others. Think about Newton's physics, his laws of motion, his law of gravitation, his mathematics of calculus. They all fit together perfectly. Each part makes the others more certain. That's integration. When a theory has parts that contradict each other or parts that just sit there without connecting to anything else, that's a red flag. Third, the scope of your claims must match the range of your integrated data. You can't leap further than your evidence supports. But here's the key. When you truly understand causal relationships, when you've integrated your knowledge properly, you can legitimately make very broad claims. Newton could claim universal gravitation because he understood the essential nature of mass and gravitational force. His scope matched his depth of understanding. These three criteria, derivation, from observation, integration into a coherent whole, and scope matching evidence, they're the test for valid induction. And when you apply them, you can see exactly where modern physics went wrong. Now, to really understand why induction has been so misunderstood, we need to look at two philosophical errors that have dominated Western thought: rationalism and empiricism. Rationalism says that true knowledge comes from pure reason, independent of observation. The rationalist thinks you can figure out how the universe works just by thinking hard enough. Descartes was a rationalist. He tried to deduce the nature of reality from the single premise, I think, therefore I am. The problem with rationalism is obvious. You can construct beautiful logical systems that have nothing to do with reality. Medieval philosophers spent centuries debating how many angels could dance on the head of a pin. Logically rigorous, completely disconnected from the world, empiricism swings to the opposite extreme. The empiricist says only direct observation counts. Don't generalize, don't theorize, just collect data. The problem with empiricism is that it paralyzes science. If you can't generalize beyond your observations, you can't have laws, you can't predict anything, you're just a data collector, not a scientist. David Hume was an empiricist, and that's exactly why he concluded that induction was unjustified. If you can only know what you directly observe, then of course you can't justify claims about what you haven't observed. But here's the thing. Both rationalism and empiricism are wrong, and they're wrong for the same reason. They both divorce thinking from reality, the proper approach, which is developed in the logical leap building on Ayn Rand's work, recognizes that valid knowledge requires both observation and reasoning. You start with observations. You identify causal relationships through careful analysis. And then you generalize, but only as far as your causal understanding permits. This isn't rationalism because you're always grounded in observation. This isn't empiricism because you're actively reasoning about causes. It's a third option that integrates what's true in both while avoiding their errors. And this is the method that actually built science. Galileo, Newton, Dalton, they weren't rationalists or empiricists. They were something else entirely. One of the most powerful insights in this analysis is that proper induction is inherently self-correcting. When you follow the right method, when you ground your generalizations in causal understanding and integrate them with everything else you know, errors tend to get caught and fixed. Here's why. When you make a valid induction, it connects to other knowledge. It makes predictions, it has implications, and if something is wrong, those connections will eventually reveal the problem. Remember the discovery of Neptune? Astronomers noticed that Uranus wasn't moving exactly as Newton's equations predicted. They had two options. They could conclude that Newton was wrong, or they could conclude that something else was affecting Uranus. Because Newton's laws were so well integrated with everything else in physics, because they had been confirmed in so many ways, astronomers trusted the laws and looked for another explanation. And they found Neptune. That's self-correction in action. The integrated nature of valid knowledge helps you identify and fix errors. But here's the flip side. When you abandon proper method, when you adopt theories that aren't grounded in causal understanding, you lose this self-correcting ability. If your theory doesn't make testable predictions, you can never discover it's wrong. If your theory isn't integrated with other knowledge, there's nothing to catch your errors. You can wander off into fantasy and never find your way back. This is exactly what's happened in parts of modern physics. Theories that can't be tested, interpretations that deny causality, mathematical structures with no connection to observation. There's no mechanism for correction because there's no proper method being followed. All right, let's bring this home. Because this isn't just about physics, this is about how you think. Every day you make inductions, you generalize from your experiences, you form beliefs about how the world works, about what people are like, about what will make you happy or successful. And most of the time you do this without any conscious method. You just absorb patterns and assume they'll continue. But what if you applied the principles we've been discussing? What if you demanded causal understanding before generalizing? What if you integrated your beliefs into a coherent whole? What if you matched your certainty to your actual evidence? Think about it. How many of your beliefs about yourself are based on real causal understanding versus just pattern matching from a few experiences? Maybe you tried something once, failed, and concluded, you're bad at it. But did you understand why you failed? Did you identify the actual causes, or did you just make a leap based on one data point? Maybe you believe certain things about relationships, about money, about what's possible for you. But are those beliefs grounded in genuine understanding, or are they just generalizations from limited experience? The method that built modern science is available to you. You can apply it to your own life. Start with observations. Ask why, identify causes, integrate what you learn, and only then generalize, and only as far as your understanding permits. This is how you avoid the traps that catch most people. The trap of overgeneralizing from limited experience. The trap of holding contradictory beliefs. The trap of certainty without understanding. The scientists who changed the world weren't smarter than you in some mystical sense. They had a method, and that method is learnable. What I find compelling about this book is the historical analysis holds up. Galileo, Newton, and the great scientists of the past really did use the method described here. They really did demand causal understanding. They really did integrate their discoveries into coherent systems. And the diagnosis of modern physics resonates with concerns that many physicists themselves have raised. The lack of progress in fundamental physics over the past several decades is real. The disconnect between theory and experiment in some areas is real. The proliferation of untestable theories is real. At minimum, understanding this perspective will make you think differently about knowledge, about science, about your own reasoning. And that's valuable regardless of where you ultimately land on the philosophical questions. So here's where we are. For 400 years, a powerful method of thinking built everything we call modern science. From Galileo's falling objects to Newton's universal gravitation to the atomic theory of matter, the pattern was the same. Observe carefully. Identify causes. Integrate your understanding, and then make the leap. This method was never fully articulated. It was practiced by geniuses but not explained in a way ordinary people could learn, and when philosophers attacked it, when they said induction was unjustified, science had no defense. The result was a slow drift away from the method that worked, a drift toward pure mathematics detached from reality. A drift toward theories that can't be tested. A drift toward giving up on understanding. But the method still exists. It can be recovered, it can be applied not just in physics but in your own life, your own thinking, your own quest to understand the world. The logical leap isn't a leap into the dark, It's a leap grounded in causal understanding, integrated with everything you know, matched to the evidence you have. It's how human beings actually gain knowledge about reality. And that's something worth understanding. I'll see you in the next one.